Reinforcing an idea that we've seen previously. Just kind of repeating the same idea because we still need to get used to it. We have a point x0, y0 in the xy plane, and we move along the vector delta xi plus delta yj. We move some delta x in the I direction and some delta y in the j direction, and we want to ask by how much the value of z equals f of xy changes. Now implicitly we got a function f of xy defined in the neighborhood at least of x0, y0. Okay, if we move a distance delta x in the I direction, then what's the change in z going to be due to that motion? Well, it's going to be equal to the slope of the graph in the xz plane multiplied by delta x. The slope of the graph is fx. Now, implicitly, fx is evaluated at the point x0, y0. So, whatever the slope in the x direction is at the point fx, y0, slice the graph of the surface, you get a curve in an xz plane, a plane parallel to the xz plane, xz coordinate plane, and that graph is going to have a slope at the point right above this one. Multiply that slope by delta x, you find out approximately what the change is going to be in z due to that motion in the x direction. You do the same thing in the y direction. Slice it with a plane parallel to the yz coordinate plane. That takes your graph and gives you a curve of intersection. Slope of that curve at the point above x0, y0 tells you the rate at which z changes with respect to y. You multiply, and that's your partial derivative with respect to y evaluated at this point. Multiply that by delta y. It gives you the change in z due to the change in the y direction. The total change in z is going to be approximately equal to the sum of the two changes. Now, these are approximate equalities, and I think I've either written them as equalities, pretty clearly written as equalities, but they should be approximate. So let me change that. Okay. Actually, if you move from here to here, you do get a change that's very close to this. Why, in moving from here to here, do you get a change that's close to the change you get from here to here? Well, the reason is that delta x is presumably small, and if delta x is small enough, then your slope in the y direction isn't going to have time to change by much when you get here. So we're going to say then, and similarly, your slope above in the plane that slices the graph here isn't going to vary much from the slope that you get here. The slope that you get at this point won't be much different than the slope you get here. So when we add the delta z hat, delta z tilde here to the delta z hat that we get here, we get a decent approximation of delta z to the extent that delta x and delta y are both small enough. Okay, so the delta z we get is equal to fx delta x plus fy delta y. Again, fx evaluated at x0, y0, fy evaluated at the same point. Okay, because delta z hat is fx delta x, delta z tilde is fy delta y. And that we have observed to be equal to the dot product of fxi plus fyj with delta xi plus delta yj. Very clear that this dot product gives you this. If we define our del operator as we have as partial with respect to x times I plus partial with respect to y times j, then applying that to f just gives us this. So this is del f dot del xi plus delta yj. So that's your delta z. It's equal to, approximately equal to del f, which is a gradient of f, dotted with your vector delta xi plus delta yj. Okay, well, if we divide delta z by delta s, the delta s that we get, of course, is the distance we travel on the hypotenuse, and that's going to equal the square root of delta x squared plus the square root of delta x squared plus delta y squared. So delta z over delta s is going to be the del f dot this vector divided by its magnitude, the delta xi plus delta yj vector divided by delta s. But then delta s is just delta x squared plus delta y squared. So now what do we have? We have the gradient vector dotted with a unit vector. Dividing a vector by its magnitude gives us a unit vector. So that's a del f dot u, gradient of f dotted with a unit vector in the direction you want to move. Okay? So our delta z over delta s then is, that should be approximately equal to this, which means that the delta z over delta s is approximately equal to delta f dot u, and in the limit as delta x and delta y go to 0, this approximation becomes accurate, and we can say that I'll write it here, that dz ds equals del f dot u, where del f is the gradient of f evaluated at the point in question, and u is the unit vector in the direction you want to go. Now, another way to write that unit vector is to specify the unit vector. It's just a unit vector in the direction theta equals inverse tangent of delta y over delta x. So, theta being the angle with the positive x direction, measured counterclockwise from the positive x direction. We see that this gives us the rate at which the value of the function changes as we move in the direction theta relative to the positive x-axis. And this is called the directional derivative. Of f in the direction of u.